Addressing code violations in irrigation pump systems at a high scale involves several options, each with varying costs and levels of comprehensiveness. Let's explore three distinct approaches. Firstly, the comprehensive retrofit. This is the highest cost option. It entails replacing the existing 800 amp bi-line panel with a new, code-compliant panel. This also involves upgrading the feeder cable from 100 amp single-phase to 200 amp three-phase, replacing the two-pole panel with a four-pole panel rated for 480 volts, and upgrading all circuit breakers and wiring to meet current code requirements. Secondly, the partial retrofit and code compliance approach. This option has a medium cost. Here, you keep the existing 800 amp bi-line panel, but add a supplemental 200 amp three-phase feeder to power the pump systems, replacing the two-pole panel with a four-pole panel rated for 480 volts and upgrading all circuit breakers and wiring associated with the pump systems to meet code requirements. Thirdly, the code compliance only option. This is the lowest cost option. This option involves keeping the existing panels and wiring as is, but adding labels and signage to indicate any non-code compliant conditions and correcting any immediate safety hazards such as exposed wiring or overloads. Based on the details, the partial retrofit and code compliance option seems like the most balanced approach, addressing the code violations while minimizing costs. This option provides the necessary upgrades to the pump systems and electrical infrastructure without replacing the entire main distribution panel. There are also additional considerations such as electrical codes and permits. It is critical to ensure compliance with local electrical codes and obtain necessary permits. Load calculation should also be performed to determine the appropriate feeder size and circuit breaker ratings. Planning for site access and scheduling work outside of school hours or during breaks is important, and arranging for electrical inspections before and after completion of work is essential. The National Electrical Code, or NEC, provides guidelines for safe electrical installations. The 2008 edition would apply if that is the code cycle in effect at the time of the work. Some key areas to consider are firstly, Article 220, which covers load calculations for branch circuits, feeders, and services. This article helps determine the appropriate size of conductors and overcurrent protection based on the expected load. Secondly, Article 250 addresses grounding and bonding requirements, ensuring a safe path for fault current to return to the source, reducing the risk of electrical shock. Thirdly, Article 310 provides tables for allowable ampacities of insulated conductors, taking into account factors like conductor size, insulation type, and ambient temperature. For example, NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and temperature rating. Fourthly, Article 430 covers motors, motor circuits, and controllers, which is relevant for the pump systems. It includes requirements for motor overcurrent protection, disconnecting means, and control circuits. Fifthly, Article 440 covers air conditioning and refrigerating equipment, but it may have some relevance if the pump systems are used for cooling purposes. Sixthly, Article 600 addresses electric signs and outline lighting, which may be relevant if there are any illuminated signs associated with the irrigation system. Seventhly, Article 680 covers swimming pools, fountains, and similar installations. While not directly related to irrigation, it provides valuable insights into electrical safety around water. Specifically, Part 2 of Article 680 addresses permanently installed pools and spas, outlining requirements for bonding, grounding, and GFCI protection. Part 3 covers permanently installed spas and hot tubs with similar safety measures. Part 5 addresses fountains, decorative pools, and reflection pools, with specific requirements for underwater lighting and equipment. Part 7 covers hydromassage bathtubs, which might not be directly relevant but provides context for electrical safety in wet environments. Part 8 addresses spas and hot tubs installed indoors, emphasizing ventilation and moisture control. Lastly, Article 700 covers emergency systems, which may be relevant if the irrigation system is critical for fire suppression or other emergency purposes. Several other codes exist, which are firstly NFPA 70E, which covers electrical safety in the workplace. This standard provides guidance on safe work practices for qualified electrical workers, including lockout/tagout procedures, personal protective equipment, and arc flash hazard analysis. Secondly, ANSI standards, which are developed by the American National Standards Institute. These standards cover a wide range of electrical equipment and systems, ensuring safety and performance. Thirdly, UL standards, which are developed by underwriters' laboratories. These standards are used to evaluate the safety of electrical products and components. Fourthly, IEE standards, which are developed by the Institute of Electrical and Electronics Engineers. These standards cover various aspects of electrical engineering, including power systems, telecommunications, and computer engineering. Fifthly, state and local building codes, which are based on the International Building Code (IBC) and the International Residential Code (IRC), which incorporate electrical requirements from the NEC. Before starting any electrical work, it's essential to review the project scope, consult with qualified electricians, and obtain necessary permits from the local authorities. Regular maintenance and inspections can help identify potential issues early on, preventing costly repairs and ensuring the long-term reliability of the electrical system. Properly sizing conductors is crucial to ensure the safe and efficient operation of electrical circuits. The National Electrical Code (NEC) provides guidelines for determining the appropriate conductor size based on the applied load, ambient temperature, and other factors. The ampacity of a conductor is its current carrying capacity, which is the maximum amount of current it can safely handle without overheating. NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. The allowable ampacity of a conductor must be greater than or equal to the calculated load current. This ensures that the conductor can handle the expected load without exceeding its temperature rating. Voltage drop occurs when the voltage at the load end of a circuit is less than the voltage at the source end. Excessive voltage drop can cause equipment malfunction, reduced performance, and increased energy consumption. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger conductors or shorten the circuit length. Ambient temperature affects the ampacity of conductors. As ambient temperature increases, the ampacity of a conductor decreases. The NEC provides correction factors for adjusting ampacity based on ambient temperature. When conductors are installed in raceways or conduits, their ampacity is reduced due to heat buildup. The NEC provides adjustment factors for dirting conductors in these situations. Continuous loads are loads that operate for 3 hours or more at a time. The NEC requires that conductors supplying continuous loads be derated to 80% of their ampacity. When sizing conductors, consider future load growth. Oversizing conductors can provide additional capacity for future expansion. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, while bonding ensures that all metal parts of an electrical system are at the same potential. The grounding electrode conductor connects the grounding system to the earth. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The equipment grounding conductor connects the metal parts of electrical equipment to the grounding system. The size of the equipment grounding conductor is based on the size of the circuit overcurrent protection device. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electrical shock. They detect ground faults and quickly interrupt the circuit. GFCIs are required in wet locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are designed to protect against electrical fires. They detect arc faults and quickly interrupt the circuit. RFCIs are required in many areas of the home, such as bedrooms and living rooms. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. They divert surge current to ground, preventing damage to sensitive electronics. SPD are recommended for all electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. They interrupt the circuit when the current exceeds a safe level. Circuit breakers are resettable overcurrent protection devices. They can be manually reset after an overload or short circuit. Fuses are one-time overcurrent protection devices. They must be replaced after they blow. The interrupting rating of an overcurrent protection device is the maximum amount of current it can safely interrupt. The interrupting rating must be greater than or equal to the available fault current at the point of installation. Short circuit current rating, or SCCR, is the maximum short circuit current that a component or assembly can withstand without causing a fire or electrical hazard. It's critical to select components and assemblies with SCCRs that meet or exceed the available fault current at the point of installation. The available fault current is the maximum current that could flow in a short circuit. It depends on the impedance of the power source and the impedance of the circuit. A short circuit study is an engineering analysis that calculates the available fault current at various points in an electrical system. This study is essential for selecting components with adequate SCCRs. Properly labeling electrical panels and equipment is essential for safety and maintenance. Labels should clearly identify the purpose of each circuit breaker, the voltage and amperage of the circuit, and any other relevant information. The label should be durable and resistant to fading or damage. Regular inspections and testing of electrical systems are essential for ensuring the safety and reliability. Inspections should be performed by qualified electricians. Testing should include insulation resistance testing, ground impedance testing, and circuit breaker testing. Infrared thermography is a non-invasive method for detecting hot spots in electrical equipment. Hot spots can indicate loose connections, overloaded circuits, or other problems. Power quality monitoring is the process of measuring and analyzing the characteristics of electrical power. Power quality problems such as voltage sags, voltage swells, and harmonics can damage electrical equipment and disrupt operations. Energy efficiency is the process of reducing energy consumption. Energy-efficient electrical equipment and practices can save money and reduce environmental impact. Variable frequency drives, or VFDs, are used to control the speed of motors. VFD can save energy by reducing the speed of motors when they are not needed to operate at full speed. LED lighting is more energy efficient than traditional incandescent and fluorescent lighting. Power factor correction is the process of improving the power factor of an electrical system. A low power factor can increase energy consumption and reduce system capacity. Electrical safety training is essential for all employees who work with or around electrical equipment. Training should cover topics such as lockout/tagout procedures, arc flash hazards, and electrical safety work practices. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve isolating the equipment from its power source and placing locks and tags on the disconnecting means. Arc flash is a dangerous electrical hazard that can occur when a short circuit or arc fault creates a high-energy explosion. Arc flash can cause severe burns, injuries, and even death. Personal protective equipment, or PPE, is used to protect workers from electrical hazards. PPE includes items such as insulated gloves, safety glasses, and arc-rated clothing. Safe work practices are essential for preventing electrical accidents. These practices include always de-energizing equipment before working on it, using insulated tools, and maintaining a safe working distance from energized parts. In addition to these general electrical guidelines, several specific requirements apply to irrigation systems. These requirements are designed to ensure the safety of people and equipment around water. Ground fault circuit interrupter, or GFCI, protection is required for all 120-volt receptacles that are located within 25 feet of a swimming pool, fountain, or similar water feature. Bonding is required for all metal parts of an irrigation system, including pipes, pumps, and control panels. Bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. Wiring methods for irrigation systems must be suitable for wet locations. Direct burial cables must be buried at a depth of at least 18 inches. Control panels for irrigation systems must be weatherproof and located in a safe and accessible location. Overcurrent protection is required for all irrigation system circuits. Surge protection is recommended for all irrigation system equipment. Regular maintenance and inspections are essential for ensuring the safety and reliability of irrigation systems. Consult with a qualified electrician to ensure that your irrigation system meets all applicable electrical codes and standards. Performing load calculations ensures the electrical system can handle the anticipated demand safely. Load calculations involve determining the total current draw of all electrical devices connected to a circuit or system. The NEC provides guidelines for calculating the load for various types of equipment. The first step is to determine the volt-ampere or volt-amps rating of each device. The volt-amps rating is the product of the voltage and current of the device. For example, a 120-volt device that draws 10 amps has a volt-amps rating of 1200 volt-amps. The next step is to apply demand factors to the volt-amps ratings. Demand factors are used to account for the fact that not all devices will be operating at the same time. The NEC provides demand factors for various types of loads. For example, the demand factor for general lighting in a dwelling unit is 100% for the first 3000 volt-amps and 35% for the remainder. After applying demand factors, the total volt-amps load is calculated. The total volt-amps load is then divided by the voltage to determine the total current load. For example, a 240-volt circuit with a total volt-amps load of 4800 volt-amps has a current load of 20 amps. The conductor size must be selected to carry the total current load safely. The NEC provides tables for determining the allowable ampacity of conductors. The overcurrent protection device must be selected to protect the conductors from overload. The overcurrent protection device should have a trip rating that is no greater than the ampacity of the conductors. In addition to the NEC requirements, local codes and regulations may also apply. It is important to consult with a qualified electrician to ensure that your electrical system meets all applicable requirements. Here's a more detailed breakdown of calculating conductor ampacity and voltage drop. Firstly, conductor ampacity is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. The NEC provides ampacity tables such as Table 310.15b16, which list ampacities for various conductor sizes, insulation types, and temperature ratings. These tables assume specific conditions such as an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit and no more than 3 current-carrying conductors in a raceway or cable. Correction factors are applied when the ambient temperature exceeds 30 degrees Celsius. Adjustment factors are applied when there are more than 3 current-carrying conductors in a raceway or cable. These factors reduce the conductor's ampacity to prevent overheating. The corrected ampacity is calculated by multiplying the table ampacity by the correction and adjustment factors. This ensures the conductor is appropriately sized for the actual operating conditions. Secondly, voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce efficiency, and shorten the lifespan of electrical devices. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop can be calculated using Ohm's law and the conductor's resistance. Factors that influence voltage drop include the conductor's length, current, and resistance. Longer conductors, higher currents, and higher resistance increase voltage drop. To minimize voltage drop, use larger conductors, shorten the circuit length, or reduce the current. To calculate the approximate GPS coordinates for Portage, Indiana, based on available information. Please note that this is an approximation and the actual coordinates may vary slightly. Latitude is approximately 41,564 degrees north and longitude is approximately 87.1839 degrees west. Always verify precise locations using reliable mapping tools for accuracy.